Hey, good afternoon, everyone. Welcome to our seminar this week. We have Carlos today, Carlos Zapata-Carratalá, if I'm pronouncing that correctly. It's not that difficult. We just established that we met briefly at ICGT recently, but so he is at the Wolfram Institute, which is basically doing computational physics, as far as I understand. If that's, I mean, he's going to tell us more in detail about what that involves. But as one of the methods they have there in order to model the computations, they use graph rewriting. So we've had a couple of talks by representatives of that institute already here, including Stephen Wolfram himself. So we're going to go into that in more detail, of course. And he's also leading a Society for Multidisciplinary and Fundamental Research, which we may also hear about. I'm not entirely sure, but I found that interesting when we talked about it earlier. So yeah, without me sort of spending any more time, please, Carlos, take it away.
Well, thank you very much. It's a great pleasure to be in the graph rewriting seminar in the end, because I've been following since I first got interested in this topic a couple of years ago. I've been watching most of them and joining some of the sessions, and I always thought, okay, at some point it'll be great to share the sort of ideas that I've been working on in the last couple of years. So my first disclaimer is I come to graph rewriting in a very oblique way, perhaps, maybe not so oblique for people who might have had some experience with algebraic graph rewriting, things like that. But I'm really not an expert, so I'm here mostly to absorb as much as possible from your community and to try and clarify my ideas by sharing them. So yes, so thanks for the introduction, Heiko. I think I will basically just say that the stuff that I'm doing is all gathered in one website. It's called arity.science, easy to remember. You'll find sort of all the ramifications of the research that I've been working on in the last 2-3 years. And it's, in a sense, the scope of the project is very broad. As this says on the screen, it's all kind of compositional structure of higher order systems, which is very, very broad, obviously. But one aspect of it has to do explicitly with the things that concern us today. And so for that, I want to explain how I came to this idea of graph rewriting in the first place, or hypergraph rewriting more specifically. So it all began with a question about associativity in algebras. So I was a PhD in mathematical physics. I was studying systems that generalize classical mechanics and quantum mechanics. So I was looking at Lie groupoids, Lie algebroids, Poisson structures, these kinds of things. And so at the heart of all these structures were Lie algebras. They were relatively, in modern physics, very well understood, right, in terms of the scope and the classification and all manner of details. So one day I was talking to my supervisor, and he happened to have worked on ternary Lie algebras for a few months, some time before, and he told me about it. I was like, interesting. I've been thinking about the generalizations of Lie algebras in all these ways in which you generalize the moment map, the anchor map, all these different ways, and then suddenly there was the generalization in the arity direction that I just never really thought of. So I got enticed by this idea of what a ternary Lie algebra should be. And so my immediate intuition went to the question, okay, I know that a Lie algebra is the infinitesimal counterpart of a Lie group that somehow nicely models smooth symmetries, continuous symmetries in usual geometry. So my natural question was, what is the ternary analog of a Lie group, right? So what is the smooth object that will integrate something like a ternary Lie algebra, which, by the way, are very well understood relatively as well. In the literature, they are called Filipov algebras sometimes, and there's a sizable literature about ternary Lie algebras. And to my surprise, there was no literature on the objects that integrated 3 Lie algebras. And so this was, by the way, 3 Lie algebras not to be confused with Lie 3 algebras, which are a different thing. So these are ternary Lie algebras, right? So a bracket with 3 entries and satisfies the Jacobi identity as you expect, just this distributivity kind of identity. So I was very surprised, and I even found some papers that explicitly claimed or stated that the problem of integration of ternary Lie algebras was essentially untackled, not only open, but untackled. So I got very curious. So I started to think, okay, what is ternary associativity? How should I think of, because typically one thinks that the Jacobi identity of a Lie algebra comes from the associativity axiom of the Lie group, or a combination of invertibility and associativity, but actually boils down to associativity mostly. And so I thought, okay, how do I extend this axiom to these higher algebras? I thought I will just find textbooks on ternary groups and just be able to read and learn about them. Turns out that wasn't the case. And so through that, I ended up, as I'll show you in a second, coming to hypergraph rewriting. And so to tell you exactly how that happened, I need to tell you the one anecdote that it's very dear to my heart, because it actually coincided with how COVID affected a lot of mathematical collaboration. So I had been thinking, so this was very much a COVID times, COVID era problem, because it was a Zoom call with my supervisor, and it was me in the boredom of lockdown thinking, okay, I'm going to do some ternary algebras for fun, because I was, not very busy with other things at the time. And so it was around that time that I started collaborating with some other people who knew about algebras called semi-heaps, which satisfy this axiom that is on the screen. So it might look like associativity, but if you look closely, the middle bracket here is inverted, right? So you have DCB instead of BCD. So this is very close to being associative. In fact, any group with the operation A, B minus 1C, so this sort of conjugated triple product, satisfies exactly these axioms. So I was then very curious, okay, how can I understand this associativity? I mean, this associativity has some literature. People have worked on this semi-heaps, heaps structures. And I wanted to have when I say understand, I really mean I wanted to have a mathematical theory that allowed me to see associativity as a very concrete fact, and not just something that I impose by hand, because then it's useful for what I derive. And so I was in chats with people in the Wolfram sphere, and that's how I eventually got to interact more with them as well, that told me about, graph theory, graph rewriting, and so on. I mean, I am a very traditionally physicist, geometer kind of training before this time. So I had never seen the graph theoretic definition of path completion or transitive completion and things like that. So to me, although it was intuitive and I sort of knew the concept, I had not pondered about it. So at that time, I realized, okay, there is a way to understand associativity that is extremely primitive in some sense. If you take a graph and you look at paths, the property of associativity of the matrix multiplication of the adjacency matrices of these graphs is essentially down to the fact that I am looking at the transitive completion of the graph, right? So I thought, okay, this is an interesting it's an interesting way to encode associativity. So I'm going to see if I can stretch that to the ternary setting. And so I was looking at these axiom once, and I say this is an interesting anecdote for COVID, because it was the first time that we met in person after a couple of years of online interaction. And we had a blackboard and we had a paper printed out, and I looked at the blackboard, I saw the formula, I looked at the paper printed out, and I thought, oh, I can see this pattern that if I put triangles in this particular, with the three arguments being each of the vertices, I can fit into a pattern that is going to analogously show me graphically, like the way you show graph completion or transitive completion. So this was the diagram that I sketched in that blackboard at the time, which is basically just triangles put together in a way that if you rewrite a pattern that is consistent throughout, you get something like the axiom that you have above. So I will actually show this example computationally later on, like implemented in our hypergraph rewriting functions. But this was the example. So we saw that there was some form of diagrammatic rewriting sort of system that allowed us to encode what previously was just a weird, quirky, little known ternary algebra called semi-heaps, right? So that was we said that in our paper a couple of years ago, and that was sort of the beginning. It was very sketchy. I don't know if we mentioned hypergraphs explicitly or not. I was not really aware of any work in these areas. So it was very speculative at the time. But coincidentally, as I said, some of these people were in the Wolfram sphere. They were co-organizers of a summer school and so on. And Stephen himself and the collaborators was starting the physics project, and it was very much based on hypergraph rewriting. So eventually I came to become part of the Wolfram Institute, and where this was sort of a foundational topic there. And that's how I got very interested in this. And so at some time, maybe a year ago or a year and a half ago now, I decided that the best course of action after struggling with these higher-arity algebras for a couple of years was to devise a automated rewriting computational framework to be able to find out things about these algebras. In the same way that it was easy to see, as I will demonstrate with some examples, for smaller algebras like associative, category-like constructions and things like that, I wanted to see if I could develop a more general and more parsimonious approach to just general diagrammatic algebras. Anyway, so this is what I'm going to try and communicate today. But for that, I'm going to first introduce the work in progress, the Wolfram Institute. We were working on this hypergraph paclet that we are implementing. So, by the way, Nick Merson is my colleague at the Institute, is here in the Zoom room. So if there are some technical questions, he might be more suited than me to answer later on. But basically, the point of the package of functions that we're developing is, on the one hand, to extend the graph functionality of Mathematica that already exists and is quite well polished. On the other hand, is to implement, so to not just naively implement undirected hypergraphs or some basic hypergraphs, but have some general notion of hypergraphs in which the hyperedges have arbitrary symmetry. So they can have any sort of internal structure. In a way, they can be sort of hypergraphs in a sense, in that you are encoding a hypergraph in each hyperedge potentially. But in principle, what we are interested in is things like undirected, directed, cyclic, input-output, so many-to-many, and some classes of symmetries that are more typical and more generally useful. But in principle, we would like to have a generalistic sort of parsimonious approach to hyperedge symmetry. Then, in my side of the task, I guess, is that I want this packlet of functions to be the basis for diagrammatic computation and some kind of very general diagrammatic computation. So, in particular, recovering things like categories and higher categories and all these things that are very common in modern mathematics. And finally, a part of my motivation is that it should have an intuitive graphical interface, because I think one of the core values of dealing with hypergraphs or diagrams in general is obviously that you have direct cognitive connection with the spatially distributed information. So if we had a function package that basically just crunches diagrams in some coded way, it'll be nice because the computation will happen, but somehow the user experience will be a little bit lost there. And most mathematicians, will have some barrier of entry to learn the code and everything. And I think that part of the value is that many of these diagrams are very immediately grasped by sight. And so we are part of the challenge is to have a relatively smooth graphical interface to at least some small diagrams. Okay, so let me show you the basics of the package here. I think I can share this. Everyone is seeing the notebook, right? Okay. So as I say, this is a work in progress with Nick Mercer at the Wolfram Institute. And I'll just go over the basics of what this looks like. So we have a hypergraph object. You specify a list of vertices, and these can be any expressions really. You specify a list of hyperedges, and by default, the functions render an undirected hypergraph. Now, you can specify symmetry for the edges. So you can specify vertex labels as well. You can specify the edge symmetry basically by associating ordered, unordered, or in principle, we are aiming to have a full sort of group of generators of symmetries of all your elements, pair edge. So we want eventually to have that degree of granularity of symmetry encoding. You can do it edge by edge, or you can do it sort of hypergraph wide, but just setting the whole thing to ordered.
Can I ask a question here?
Yes, please, of course.
To understand your notion of symmetry. So if you have unordered hyper edges, obviously the symmetries are all already there, right? So
yes.
So just let me try to rephrase what you're saying, or try to this, and then you tell me whether I'm right. So,
yes.
So what you're saying is, if you take an ordered hyper edge, you can still say that certain nodes, certain attachments of that hyper edge are exchangeable. So you get a kind of partial symmetry
Yes,
that you specify explicitly rather than the arbitrary symmetry that you get in the unordered case. Is that what you're aiming at?
that's basically what we are aiming at. Yes. So we want to specify exactly. So at the language level, we're always going to have to specify a tuple effectively, because we will have to specify a list of vertices in an edge. So the way we sort of overcome that is that we want to encode the fact that those vertices might have some redundancies. So, for example, in the case of unordered, which is what we have by default because it's the one that we're using the most and the most parsimonious in some sense, has all the possible n factorial symmetries of all the vertices, right? So obviously it is a challenge to, for example, write algorithms to do typical search or canonicalization or different operations with the hypergraphs once your symmetries are diverse, because sometimes they don't play nicely with each other. So that's one of the big challenges that we have to overcome in the future. At the moment, we're focusing on directed and undirected as two extremes of the symmetry spectrum, and making sure that they work together, not only on their own. But that's the understanding, that you would have each of these. So this is never going to, at the level of language, for us, this is always going to be like that. We're going to have an ordered list of vertices, and so we're going to append some labeling like this, some sort of annotations on the edges that will specify the symmetry type in some sense, and it will affect only those vertices. Right?
Okay.
Right. Yeah, thanks for the question. And well, on that note, actually, this way of appending annotations to the edges is actually the main way in which, for the diagrammatic calculus side of things and the pattern matching side of things, we are mostly working on. So the edge labels is basically how you populate the hypergraph with data. So something that I want to mention here, because it's quite relevant, is that my approach to using hypergraphs as diagrams for computation is not so much that we want the software to analyze the hypergraphs efficiently or to have some sort of hypergraph analytics, but it's more that the hypergraphs themselves need to become the data structures that are going to support computation. So it's a change. Obviously, hypergraph analysis is going to be very relevant for that, but it's a change in perspective a little bit. Is that for us, this thing here, this hypergraph, with a few binary and ternary edges, that is to us like a list in Wolfram language, for example, or in any other language, right? So we want to generalize in that way, and so Mathematica is quite flexible for that. That's why we're sort of prototyping it here. I also want to say that this could become, this could interact with other languages, and we could have libraries that talk to other existing very refined algorithms that are already out there. But this is very good for our sort of prototyping, because the edges can be labeled with arbitrary expressions. So I can put any expression I want. I can do pattern matching with this underscore. I can do things that actually compute on the edges themselves. So it's very flexible. So I will use just the pattern matching in this talk and for my purposes and my algebraic interests. But the functionality is there in principle. And well, there's some options for plotting. I'll actually be using the dark theme for the algebraic part, because it looks more like a blackboard and it feels a contrast to me. So I like it. So this is what it looks like. How do you generate and edit hypergraphs? Well, we have some random generation. So some basic, you specify maximum number of vertices, and then you specify a arity signature in a sense. So this is saying that there should be one unary edge. This is saying there should be two binary edges, and it's saying that it should be one ternary edge, right? So as you can see, there's two binaries. There's one unary there, a little circle. There's two binaries, and there's one ternary, right? So you can specify some options. You, for example, can demand the hypergraph to be simple, and in this case, it becomes unconnected, and you could say true, all, or false to specify that you want all of them, only the unconnected, only the connected, and so on. And most importantly, we have some systematic enumeration. So for now, we have separated enumeration on ordered and unordered. So for example, if I wanted to enumerate all the hypergraphs up to 4 vertices, that are by default connected and simple. By the way, that's the default options. That have two unary edges and two binary edges. Well, you get this list of graphs with unary edges. Similarly, here another example: enumerate hypergraphs. These are unordered, so they have the usual hypergraph isomorphism function in the background with the symmetries, the correct symmetries here. So it enumerates that up to 5 vertices. Here you can say all to have all the vertices that have non-empty outputs. So this is actually a very important enumeration for our early research on ternary algebras, because this is actually enumerating indirectly all the possible ways in which you can multiply ternary tensors together to produce ternary tensors. So a subset of these hypergraphs actually encode such products. Not all of them, but some of them. So anyway, so there's that enumeration functionality. As I said, you can use connected as well, false. Something that I would like to demonstrate live, although it's a little bit unstable, so I can promise that it won't crash. But we are trialing a graphic interface. As I said, for me, it's important that these diagrams, because they are small, they are meant to be sort of as closely used by mathematicians as possible to what they draw in a piece of paper or a blackboard. So let me run this. So unfortunately, it's a little bit small, but you'll get the point. So basically, you get a window where you can input vertices. So for example, I can input like that and like that. And I can press E to create an edge. And then I can edit the edge if I select it. Okay. And so I can, for example, make it order. So create a little arrow. I can maybe change the color. I can, so this one I'll it like that. And I could copy, I could write some label. For example, I could write, I don't know, edge, and I confirm, so I get a label. So basically you can edit a hypergraph or hypergraph object here in this context. So if I, for example, want to add a ternary edge over here, this one is ordered, I can select it, I can make it unordered, for example, etc. So this allows you to graphically edit hypergraphs, and you hit return, and then you have a functional hypergraph here. And importantly, any hypergraph that we have, we can right-click and we can go back to the editing. And you can tweak it this way. So as I say, it's a little bit unstable at the moment, and there's some things that need to be polished, obviously. But the expectation is that eventually you have something that feels quite organic if you want to draw some mathematical diagrams that are not computationally huge, right? So it's just much more user-friendly here. Okay, so I'm going to actually turn this off in case there's some problem later. All right, and finally, rewriting. So just to show you how rewriting works in our package currently, we can have unlabeled rewriting, which is how the Wolfram model effectively works. And so it's based, the rewriting functionality is based on that. So I guess people familiar with Stephen Stock or Jonathan Stock will be familiar with this. So this particular rule, we have something as simple as you can define hypergraph as an input, as an output, and then we simply take the hypergraph rule function to create a rule that encodes that. So it's important to note that here the left-hand side is being taken as pattern matching in the language. So this effectively have underscores for people familiar with Mathematica pattern matching. And so I'm going to show you how it works in practice, this particular rule. So this is all labeled, by the way. So this, even though they look unlabeled because they don't show the labels, the names are there. So the rule is actually the actual names, not the graphics. So you will see here. So if I draw a hypergraph like this, for example, where you can see there's a couple of patterns that would match in the top and the bottom of this hypergraph. I simply take the hypergraph and I apply to it what I call the rule, and the output of that application is essentially all the matches that would happen with a bunch of useful data that effectively will be encoding so the DPO data that everyone's familiar with here in this association of things. So you have vertices created, the edges that matched, the new vertices, the new edges, how vertices are mapped, etc. Right? So you get this all this granular information.
Quick question, sorry.
Yes, of course.
Can you go back to the rule?
Yes.
So how do you know which vertex on the left corresponds to which vertex on the right?
So graphically, so you do it by, let me just, vertex. So it just hides the labels by default graphically.
So you go by the numbers or the labels of the vertices. They basically match based on the.
Exactly. Yeah. So the label, the names of the elements. So in this case, the labels, they become the variable pattern matching.
Yeah.
So if I think the rule is going to show it, if I run it now, yeah. So it's a bit clamped, but that's how you know that the 2 is the one that you left out. And I'll actually show this much more explicitly. I was just sort of trying to show you that you can do this very generic pattern matching, and indeed it tries for all the possibilities. So there's 4 matches indeed, because you have undirected, so it has this freedom. But most relevant for us, we want to do labeled hypergraph rewriting. This is the core of my original interest, and what we've been sort of the difficulties in agreeing with a hypergraph rewriting set of functions is that the Wolfram project did not care about labels in principle. They were using hypergraphs as this aggregate substance in some sense. And for me, the labels is essentially all that matters, because hypergraphs are just the substrate where your data lives, right? So to exemplify that, I'll just use this example. So you have everything is labeled here explicitly. So I chose P, Q, R, S as vertex labels, and I chose X, Y as edge labels. Everything is. So I made the edge here X edge order, the Y edge unordered to show there's also a combination of symmetries. And I'm choosing this particular rewriting. So I'm taking the vertex that is the intermediary vertex. I'm taking it out, and I'm rewriting that edge with the labels that the edges carried. So you can see it more explicitly. I have X, Y, and Q, which is the intermediary vertex, reflected in the label for the new edge, right? So that is actually going to be kept track of. So if I define this hypergraph, for example, that has these 2 triangles and 2 lines. So this one, note that D is undirected and A is directed. There's a little arrow there. If I apply the rule to this, you will see that this one here, although I can't see it on my screen because I have the faces, but I think you can see that there is A, B, 2, because those were the specific names of the specific objects that we dealt with here. And of course, there's again 2 matches because it's undirected, so there's 2 possible orientations
Right. Another question, if I may?
Yes, of course.
So the labels look like terms. I mean, some of them anyway.
What? Sorry, I can hear you.
A in brackets, B parentheses
could you
2,
say
for
it again?
example.
I missed the question. I missed the sound.
Oh, the labels, they look like terms.
Terms, yes.
So I assume you're labeling over a term language.
Well, that's a very important question. So this one here, in principle, no. So in principle, not necessarily, right? So in here, I just used evocative language exactly to prompt your question. So thanks for that. I used evocative symbols to signify that somehow you want to maybe understand that X is acting on Y, and that's why you put X in brackets on Y, and maybe Q is the locus where that action is happening, and so you put Q in brackets. Right? So it's just evocative to that. I will go into the examples, specific examples of the actual sort of content of the talk, and there I think it will be much more clear whether we are using a term language or not. But indeed, that is a crucial point, and I'll come back to that later.
Okay, good.
Right. So anyway, this is the summary of what the hypergraph paclets can do at the moment. Again, I'm going to try to run this just to illustrate also a cool way to draw the rules. So we have an automated rule drawing. So for example, if I want to make every ternary edge, for example, into binary ones, I can just turn that up. So it copies the input. I can delete this one, for example, and I can just create a bunch of binary ones. And so, yeah, it's behaving well as long as I don't do to crazy stuff. And so if I return this is a rule that, I mean, yeah, the embedding is a little bit all over the place, but this is already a rule that is functional, and I can, take this and apply it to hypergraphs, and, I can call this rule, and I can use rule. Whoops. Yeah. Sorry. So there's some options there, but basically that's the idea that can be used with other hypergraphs. So back to let me minimize this. Back to the presentation. Right. So all of this, I motivated originally that I wanted to understand these higher-arity algebras. So what is this good for? There's this object that I am going to introduce. Actually, for those of you who saw my talk in the graph computation models in the summer, you might remember. So it's trying to be so it's a temporary name. I'm not set on this name, but we're calling it chemoids just as an evocative name. And I hope it will be clear why there's some chemistry evocations here. So really what I'm trying to define are higher-arity compositional structures. So in a way, we're trying to generalize categories in an orthogonal direction to what higher category theory usually does, which is they go into the higher homotopy direction. I like to go into the higher-arity direction. That is to say that the data structure that a morphism is, I want to generalize. So instead of being something arrow-like, I want it to be something, for example, like a NRE undirected edge-like. So to be very parsimonious, I'm going to say that I'm going to have something that I call atoms, which you should always have the category example in mind. So atoms will be like the objects, some primitive elements. There will be something like bonds, which will be data structures built from these atoms, and then from bonds you make molecules. So the molecules will be the diagrams in your category, for example. So these will be, for me, these will be simple hypergraphs from bonds. So specifically, I would probably want labeled simple hypergraphs for bonds, or what we call simply labeled, which means that the background hypergraph, the skeletal hypergraph, might be non-simple, but the labels might be unique on top of that non-simple hypergraph. So I'll get into this in a little bit. And then finally, what makes everything tick is the reactions. You have your molecules floating in your solution, and then they react somehow. So those would be the composition rules in more traditional terms. And in our context, this will be encoded as hypergraph rewriting rules. That's the expectation. So this, in principle, is something that is going to have some kind of life of its own. It's going to have some computational life of its own. It's going to have terms in some sense. The bonds and molecules a bit like terms, and the reactions are a bit like the traditional rewriting rules of those terms. But the idea is that for this to be like a category or to generalize a category, we need something else, which is something like the axioms that one typically imposes on this sorts of objects. And I'm calling that molecular integrity. There's not much meaning in that term at the moment, just to evoke the chemistry analogy. But it really has to be some kind of condition. It's not just the ingredients and the rewriting rules sort of giving way to this acyclic graphs of evolution. It's something more constrained than that. And the question that I was trying to answer since the beginning is, how do I exactly encode that constraint? Because my original question was, what is higher-arity associativity? That's effectively the question. So let me show you in detail what this means. So let me just scroll up here for a second. So I'm going to show you several examples of structures that are very well known, and some of them that would maybe be a little bit unfamiliar, and then one that is certainly going to be new to you probably, written in this labeled hypergraph way with the paclet at the moment. So this is functional at the moment. I'm not going to run it just in case, but I promise that this is actual outputs of the functions. I mean, we can try to run it, but once we're done. But for now, I'll just show you the outputs. So the unit line. So basically, what I'm going to do is I'm going to take rewrite rules, and I'm going to take particular hypergraphs, and I'm going to see what happens when we apply those rules to those hypergraphs. So very simple, but I hope it will paint a clear picture of where this can go. So the unit line is basically you have an element and you create a unit. So it's the typical unit arrow, so to speak. I call it line because it's undirected, so to distinguish it from the unit arrow that will come later. And of course, if you have an initial line, for example, and you start to apply, so in this, we're using this multi-computation packlet that was also developed for the physics project independently, just to visualize the rewriting systems in this sort of acyclic graphs of states. So if so you can very simply just specify the initial state, which is the single line here, and the line unit rule, which is this rule here. And it would just generate given a number of steps, it will generate the right kind of graph. So obviously now that you just have a line and you have a way to add unit lines, so the thing will just multiply and just grow. And there's nothing particularly interesting there. Okay, so moving on, line composition. So what about typical sort of path composition? So basically this pattern. So this is fully labeled. So P, Q, R, vertices, X and Y edges. And so if you have this particular pattern, Q is your intermediary, you do this sort of transitivity closure, and you get a new edge. So I'm gonna denote that edge by brackets XY to indicate that it's a multiset XY. So it's an unordered XY, or bag, if you like, of XY. And sure enough, if I choose the right initial condition, so the right initial state, FGH, 3 undirected edges like that, I get bag associativity. So this is the associative axiom for an abelian binary operation, obviously. So if you run the system, you would see that, I can't see it very well myself, but I hope that you get on your screen, that there is several flows, and you find in the end FGH here, but also all the possible permutations, because these things are symmetric. There's no sense of ordering, so the pattern matching is happening in all the possible combinations. But what's very important is that I begin with 3. So I begin with FGH simple undirected hypergraph on this vertices, and I end up with a bunch of hypergraphs on the same set of vertices, right? So these are all labeled edges from 1 to 4. So if I were to strip out the labels out of these hypergraphs, so if I do this unlabel operation, which is basically just deleting the labels in the data structure, you can simplify the rewriting system considerably, and you can look at this initial state and effectively find that your system is confluent, and you have some distinctive feature of your system now that more traditional rewriting systems care about. So what you find with this, we call this the skeletal diagram, or the skeletal rewriting diagram. And what this is telling you is that if you were to look at the symbolic one, or the labeled one, there's going to be some non-trivial axiom. And the non-trivial axiom basically is that all the edges that would populate the same confluent edge in the end, which is this 1-4 edge, that is a single one, confluent one, they are all somehow equivalent. They all express the same actual label, right? And this is where you really get into the weeds of whether your labels are a term language or where the subtleties there. There's something that I really want to understand better, because what is clear to me after, I hope it will be obvious after this presentation today, is that there's a pattern here, and there's clearly some substance to this, and I just want to make sure that I have the right tools to articulate the pattern. Okay, so let's see another example. This is okay, so line category means when you mix line units and line composition. So here you do get some non-trivial confluence, because you begin with a single line, you apply either the unit, so you apply, sorry, oops, for some reason it's not displacing. There it is. So you apply the unit on one side and then compose, or the other way, first compose and apply the unit. And so you do find between S and R, F1S, and you find 1RF, and originally you had F. So all those 3 edges that have different labels must be equivalent somehow, and that's of course the usual axiom of units being neutral under composition. Okay, so just to move quickly, because this is, I did the undirected example because it's a little bit simpler. So typical units in categories will be encoded now with 2 rewrite rules, because you need the outgoing and the ingoing arrow, although you might think that you can cover everything with the outgoing. For the specifics of this rewriting, we need both because it actually cares about whether the arrow was ingoing or outgoing to begin with. So if you have those two rules, so you put them here in a list, and you begin with a single arrow, sure enough, you get the similar tree of derivations there. Now, if you take composition, which is the very standard categorical composition, two morphisms x and y composed to x, y. Now I use the curved brackets so that I represent that this is a tuple. The information that is kept there is the order matters. And then sure enough, I can find tuple associativity or just conventional binary associativity by writing this particular diagram. So FGH and typical diagram in category theory. So again, if you unlabel, you would find that this is a confluent. It's a confluent diagram. It's not only confluent; it's confluent, and there is a non-trivial overlap of pattern matching in your initial state, which the multi-way system, the multi-computation package that we have allows us to see in a bit further detail exactly how the matching is happening. So we can actually extract a lot of detailed information about the sort of causality flow of these rewritings. So this is very simple, obviously, but we can see how the events connect in terms of the flow. We can create this so-called branchial graph, which is essentially just some state-wide relations about their causal dependence. So this basically is relating the two rewritten states, so 1, 2, 4, and 1, 3, 4. So these are the two states here in the middle. And so they basically, the fact that they are connected means that they had a common ancestor here, and they were rewritten from it. So we can refine that obviously to, for example, spot this idea of a non-trivial overlapping, which I hope to argue that it's actually quite important to identify something like associativity. So we get the usual neutrality of units in the other way. So the diagram is a bit bigger because the units are inwards and outwards, but same idea. Okay, so change of gears a little bit to think of now instead of a generative or reductive rule, let's think of a sort of neutral rule that just flips the direction of a morphism. So this is a typical dagger in a category. So what a dagger does is just takes the adjoint, right? So it just flips the order of the morphism. So we use the same notation here. We use this symbol for dagger, and you can see, I mean, the arrow is a little bit visually unclear, but you can see that this is going from P to Q, and this is going from Q to P, and that's all this does. There's nothing behind this. It's just changing the direction. So interestingly, with this same criterion, we get the two axioms that we typically assign to daggers. So we get involutivity on the one hand, which is a very trivial diagram because you begin with F dagger, and then F dagger dagger happens to be, again, an edge between S and R in the same orientation and so on. So if we strip out the labels, then we will just get the identity of rewrite rule, basically. And so that's why we know there'll be a non-trivial statement there. Because this is order. That's why you get sort of two steps, because you need to reverse and reverse again to get back to the same. But also we get anti-homomorphism. So if we combine the dagger rule that just flips the orientation with the arrow composition that we had from earlier, and we put them together in this list here, you will get a rewrite system that looks at familiar guesswork many students do of just like trying out different combinations of morphisms. And sure enough, you will find, where is it? So you will find over here, for example, the G dagger, F dagger between 1 and 3. And you will find, I think it's all the way over here. Yep. You have FG dagger dagger between 1 and 3, right? So that's the main. So actually, there is. Oh yeah, that's one extra step. Yeah, sorry. No, it's this one. Yeah. So FG dagger between 1 and 3 because it's directed in the right direction. So that's the usual anti-homomorphism behavior, right? So of course, this because we are still work in progress, I didn't have code to spot these exact patterns. So just extract the ones that are equivalent out of all the future states, but that should be fairly straightforward once we have this working.
Another quick question. So is the idea that your rules are always equivalences, and therefore all the different derivations that you do are basically also equivalences? or how do you conclude that? No, I can see that you do this derivation going from sort of, I mean, the kind of starting point where you have f and g to either f g dagger or then g dagger f dagger.
Yeah.
But sort of the reason why you think of this as an equation is that you consider all the basic rules already as essentially directed equations, right?
Right.
So all the nodes in your diagram here are equivalent because the rules are equivalences.
Right. So that's a very good question. I would say my answer is actually not necessarily, and the reason is that I am really looking at these rewrite systems in the most how to say light way possible. Right. I'm thinking they are as bare bones as they are, as they get. I mean, it's just this. I define. Maybe you want to define some domain of hypergraphs that you're going to populate, like directed, simple, up to RET3 or something. You constrain some kind of domain, some subclass of hypergraphs, and then within that subclass, maybe you also choose an alphabet. So you might choose a set of labels over which your hypergraphs can be labeled. But beyond that, you're just saying that your system is comprised by an initial state and a set of rules. And so my intuition here is that we want to use these systems to somehow characterize or to find instances of associativity or generalized associativity, right? So in a sense, I'm seeing all these states as formally distinct. I'm not implying any immediate equivalences or anything like that, but I know, because I know these structures, I know anti-homomorphism, I know involutivity, I know these axioms, I know associativity, I know how these structures typically work algebraically. I can spot the pattern that every time I begin with a simply labeled diagram, I apply these rewrite rules, and I get at some point during the evolution, I get on the same, so imagine that these were additive. So instead of deleting the previous input, it remains there. So it keeps on going. You would find that the ones that become non-simple, so the ones that populate the similar edge type twice or more, those are the ones that precisely have the sort of axiom information or the equation information that you're interested in. Because all these others, this is, for example, the one that I mentioned earlier that I was myself confused. I said, oh, it's this one over here that it goes FG dagger dagger. And it's like, why is it FG dagger dagger not part of the equivalence? Well, because you can see that the edge is directed from 1 to 3, and this one is directed from 3 to 1. So it actually, the equivalence only happens in the direction 3 to 1 because that's what you began with, right? So or that's the other one. The other one is 3 to 1 in here, right? As you can see, the arrow is pointing towards 1. So that's the criterion, right? So it's more of a probing mechanism more than
I understand. So my term for expressing it would be that your rewrite system, your set of rules, is more like a grammar generating a set of graphs that obviously to you have a particular meaning.
Correct.
Combine them for patterns that you're interested in, rather than implementing equations, even if some of them may be equivalences, but you're thinking about them as a generation mechanism rather than something which proves inequality. Okay.
Correct. Exactly. Yes, that's right. That's very good. Yeah, exactly. All right. So just to show you another. So now I'm going to get into a little bit more unfamiliar territory. I mean, not very, because one is just actions, but just to show you that not only homogeneous algebraic structures can be encoded in this way, but also the ones that involve different arities. So this is we're trying to recover the semi-group axiom. So the idea that you have these transitive actions, right? So you can have associative actions and transitive actions and so on. So the rewrite rule is, again, very simple. You just have a directed edge labeled by X and an undirected edge labeled by A. And here you have, as an output, an undirected edge labeled by XA. So here the notation is very suggestive because we're trying to imply that X is acting on A. So I think it's very visual because it's, in some sense, X is pulling A from this vertex to that vertex. Actually, here it doesn't show, but there's I think Nick told me if I do this. No, because this is not enabled. No, shouldn't have done that. Yeah, let's not try to do that because it might not be smooth enough for the edge. But anyway, so xa here is a label for an edge, right? So it just doesn't render the circle for some reason in this particular diagram. But so it's very intuitive, right? X pulls the unary edge A to the next vertex. It's almost like this flow of mass in graphs kind of construction. And interestingly enough, in my opinion, just by defining this rewrite rule, you simply with arrow composition that you had before, if you define this particular initial state, which is the almost smallest thing that you can do after your left-hand side of the rule, then you get action associativity. You get this idea that it's the same as compose your group elements before they act or act twice in composition, right? So the diagram is very simple. Of course, you have this one. You begin with on this side. You just apply the action of the sort of the pushing of the unary edge, and so you get here f of u, and then at the bottom you get g of f of u. But on this side, you first compose f and g. You have fg here, and then on this side you get f of g of u. And so again, I stress that if we strip out the labels, you will be able to see a confluent diagram here, right? And crucially, one that is on the same vertex. Like the final vertex is 3 in both cases, and so I have 2 expressions on 3, so you might want to detect that this is making some non-trivial statement about your terms in some sense. Okay, so that was an example of an inhomogeneous algebraic structure that involved a unary and a binary. Now let's get into the first ternary one. So this one so these are examples of semi-heaps. So these are structures that have been known for some time. In fact, they were discovered in the early 20th century, picked up by a Soviet mathematician called Wagner, and basically rediscovered a couple times along the way, but pretty much unknown for the vast majority of mathematicians. But they are, in some sense, they are very natural objects because, so the first way we encounter them is what I call the zigzag composition, which you essentially take this diagram, x, y, z, note how the y is sort of counter in direction of x and z. So there's this sort of democratic flow principle where, if x and z are going in the same direction, their final direction is x and z, right? So you collapse that direction, and if you take this longer diagram and you apply the same principle, what we get is the axiom that I showed earlier in the talk, this heap associativity. So I'll just show the diagram here. So you apply ABC here, you apply CDE here, and you apply DCB there. Now, crucially, the pattern matching in the middle is flipped because of the arrows pointing in the directions. So indeed, in the end, you get 3 edges oriented from 1 to 6 that have labels that, and that, and those are exactly the terms that appear in the equations that you had. So this was the one that we knew was possible from actually some papers in the early 2000s about semi-groups that sort of rediscovered this in a very indirect way. And so they actually technically used this diagram, although they didn't show it graphically in their paper. They actually used these diagrams these graphs as sort of ways of implementing semi-group actions. But the original one that we find out was with the fish kind of diagram. And so you can explicitly define the fish just as this particular 3-edge ternary hypergraph. Now, here's one of the subtleties. Why do I choose X, Y, Z in a tuple-like structure? That's a non-trivial issue here, because of course, the topology, it seems that the labeling that I'm choosing here, if I want the labeling to express something interesting, in particular to express semi-heap associativity, it needs to somehow know about the topology of the left-hand side. So X, Y, Z can be ordered because I can always distinguish in these kinds of hypergraphs, even when they are undirected, I can always distinguish the tail, body, and head. Right? Those are well defined as a data structure. So anyway, that's just a remark at this point, because in our mentality of just trying different initial states and different rules, sure enough, I use this longer fish, I label A, B, C, D, E, and yep, I get now more matches because there's all the symmetry that you can rotate the triangles and they still match. So for each of these, you get 4 matches because of all the internal symmetries. But the principle is the same. You get 3 ternary edges in the end on the exact same vertices, 1, 2, and 9, and the 3 different expressions depending on which path you followed in the labeled rewriting. So again, if I strip out the labels and I just write the unlabeled rewrite system, I get a confluent one. There's one in the end, right? All right, so so far, these are all structures that were known, that were relatively well understood. Maybe the semi-heaps not so much. That we can recover in this way. By the way, you can also, it's relatively easy to see that you can recover operads as a compositional structure simply by taking, so you have to define edges that are directed many to one. And so, or you can just take them directed and take that the last element of the tuple is the output. And you can see that if you, for each combination of arities of edges, you define a rule, which does what you expect, right? The operad with 3 and 2 becomes a 5 operad, and so on. That allows you to exactly find operad associativity as in the same kind of criteria. So the final example that I wanted to mention is something that we call the Bhattacharya-Messner composition. Oops, sorry. I was meant to scroll. So the Bhattacharya-Messner composition has this name because there was something they called a transitive associative structure in the early 90s in some combinatorics papers. Really, I'm not an expert on why this came to be, but this particular operation, this particular pattern of 4 loci in some space or some set, and 3 ternary relations in this particular superposition, this was known. This was or was not known, but perhaps used or identified by Bhattacharya-Messner in a 1990 paper. And ever since, it has only appeared in a couple of papers of people finding higher matrix products in higher matrix algebras. And that's how I came to know of it, because I was studying this as examples of possible ternary algebras. And so the rule is very simple. The rule, in some sense, is, in my opinion, the most direct generalization of line composition or traditional path composition in ternary hypergraphs. Because if you think that you're in an undirected world where you don't really see any directions or any order of your vertices, if you think about it, this is 3 edges that have an intermediary vertex where they meet, and you rewrite by a single vertex. So, by the way, this is unlabeled here, but this vertex here is the vertex in the middle, right? The dangling vertex is in the middle. So that's very similar to what you do in paths, right? Where you have 2 edges, one in the middle symmetrically, and you rewrite that one. So it turns out that if you write, by the way, whenever you write a rewrite rule like this, you can immediately copy a matrix multiplication out of it, because you essentially just take this as to mean the adjacency matrix of this hypergraph, and you can sort of write immediately sort of a matrix product out of the rule when you have one single edge as output. That is, because otherwise it doesn't match the sort of the operation signature. Right. So this was the one operation that was known. So in the literature, but nobody. It's an open problem whether this operation has some kind of associative behavior in some sense. So we know that it's not traditionally associative when you define it. Computer searches have been done. No associativity with 5 elements, with 7 elements, with 9 elements. It's not so clear, but it's unlikely. So it was clear that it was a mysterious algebraic structure that was genuinely ternary, very symmetrically ternary. There's no sense in which you can clearly see this as some combination of binaries. And so to me, this became kind of the holy grail of my exploration, because I wanted to, I got in touch with a couple of the mathematicians that have published on this structure in the last 5 years, and we all had a couple of meetings, and they were quite clueless, I must say. It's a very mysterious, subtle structure that doesn't seem to tell us very much. So I was expecting to maybe characterize its behavior under the same framework as all these other behaviors that I've shown you today. And so I tried.
Another question before we move on. So here you label the big the new hyper edge there with X, Y, Z with the sort of normal brackets. Does that mean it's ordered? And if yes, how do you know?
Yeah. So it's not ordered. So in fact, I was just going to live edit precisely to make that more consistent with my previous notation, because it really is a multiset X, Y, Z. It really is a bag. Yeah.
Okay, good.
Yeah. Otherwise, if you made the vertices automatic, you could see that there's an arbitrary sequencing that you can do. And in fact, that's how people use it, because they use it with matrix multiplication, and they do have to use some sense of ordering. But then they might assume that the matrices themselves are symmetrical after they choose that. But in this case, no. In this case, it's just fully symmetric. Okay, so I basically set myself the task of how do I find a initial state that is going to reveal some form of higher form of associativity, in the same way that I had to choose 3 arrows for the associativity case. I had to choose, a little bit of, not a lot of cleverness, but a little bit of invention to find, 5 triangles in this long fish kind of configuration to see semi-heaps. If I chose something else, I wouldn't see anything, right, with this criterion. So I tried to guess, and so I gave a very symmetrical kind of construction. I put this together. So this is a 9-edge hypergraph. And so I just run the system. So first I'm going to show you the unlabeled one, because this otherwise will get very big because of all the symmetries. And so the unlabeled one is simply like that. And you take this one, you have this naturally confluent system where, all these arrows is because you have all the possible permutation symmetries in each of the matchings. And sure enough, it is a confluent system. So in some sense, I found something that the unlabeled version of this clearly tells me there is something here. But then when I run the labeled one, and it's going to take a few seconds to load the graphics because there's a lot of permutations on the screen. But when I run the labeled one, I realized that, okay, so this is the first step. In the first step, you can see that all this is doing is taking each collection of 3 triangles and merging them into a single triangle, labeled by that. And so if I go all the way down to here, this is the final line, the equivalent of the final triangle. And you can see that what you have there is 3 brackets inserted in the 3 positions of the 3 arguments. And all the results is because you get all the permutations within each of the 3 brackets. Right? So it's a lot of possible permutations, right? But then I looked at it and I realized, but this doesn't have any interesting associative-like information, because all this is telling me is that I can take, if I have a 3-bracket nested, if I have 3 brackets nested in a bracket, it just tells me that I can choose whichever order of operation to get the final result, right? So it might be non-trivial in the sense that this is telling you that your language or your term language maybe has a meaning of the order of computation doesn't matter. Of course, that there's some information there, but I was sad to not find something like associativity, because it didn't give me any equations in some sense. It just told me that it doesn't matter in which order. So equationally, I couldn't write it. Right? It was just that's one element in the end. So then this is actually, I did by hand originally, this example. Before I knew of hypergraphs and before I knew of rewriting systems, this was just my way of trying to get fiddly with diagrams to understand what I was doing with matrices. And so I realized, okay, so if I'm convinced that there is probably some axiom, and we suspect that the axiom involves 9 edges, because we did a computer search for matrix multiplications in 5 elements and 7 elements, which correspond to 5-edge diagrams or 7-edge diagrams, and we couldn't find any. And it was the 5-element search was actually corroborated by another paper a few years ago. And so we think that there might be something in 9 edges. That's why I came up with some 9-edge structure here. And so I thought, okay, I don't think I can be clever enough to find it. And so I did a quick count of how many simple connected labeled hypergraphs of 9 edges there are. Unfortunately, there are about 12,500,000. So it's really quite a monstrous task to just go over all of them. So my strategy at the moment, and this is the end of the talk basically, is that we are almost done with having the functions to process this automatically. And hopefully we can start to systematically, for example, enumerate the maybe interesting ones, and there will be a few thousand instead of millions of the 9-edge diagrams, and just run these kinds of computations with the automated detection of that criterion, which is some kind of confluence modded by the fact that the pattern matching had to be. Oh, right. So I didn't mention. So what makes this different? So we know why this is not interesting from the get-go. We don't have to go all the way to see that it's uninteresting, because what makes this pattern matching different from the previous ones is that in the original state there is no edge overlap of the patterns. Right. Each pattern belongs in a disjoint component of the hypergraph. So if you can see, the hypergraph is in fact just three such diagrams put together in the sort of edges of the original one, right? So you can tell before doing the computation that this is not going to tell you anything interesting, because there's no overlap. Every single other example that we've had so far, the fish overlap in the middle, right? This body is that fish's tails kind of thing. So the arrows overlap in the associativity case. Well, this one has overlap because it's already a unary edge and it's always overlapping with what's there. The dagger is overlap because it's the same edge that is being operated. So we knew that so far, I mean, the examples that recover all the interesting algebraic structures seem to have that feature. They're not only confluent in the skeletal version of it, but they're also non-trivially overlapping somehow on the initial state. So we could know that this was not going to give us some equational statement in the end. So my punchline is basically, going back to the presentation, is now we have these tools, and now we can hopefully go for the Zapata-Carratalá mystery. Maybe we can say something definite up to some cardinality, which is already progress, I think, because we don't know anything otherwise. There is this correspondence I mentioned, that for every rule there is a hypergraph. There's a hypermatrix operation attached to it. So there's a question of how well these things are recovered, and so in particular existence and uniqueness of these structures. And by existence and uniqueness, I mean we know that associative algebras appear because you take a graph and you compose graphs in this way. You know that there are associative algebras there. We know that now semi-heap algebras appear, and involutive algebras appear, and all these semi-group actions appear. All these ways appear as hypergraph rewriting systems. The question is this all of them? Do we get some kind of uniqueness of representation? Do we miss some by using hypergraphs to represent them, and so on? So anyway, thanks very much. That's the end.
Okay, thank you very much. Any questions before I have another go? Yeah.
Well, thanks a lot, Carlos, for the talk. I was wondering, because so all the rules you showed seem to not delete any vertices. Was that right? Was it a pure coincidence? Is the implementation currently capable of doing? You said at some point briefly it was double push-out rewriting, where you traditionally have this problem when you try to delete a vertex and there's incident edges. The execution might not be possible. So is it true DPO, or is it just push-out rewriting in a sense? Because I mean, when you don't delete, it's essentially just taking a push-out with a template.
Right. So it is possible to delete, and in principle we can. So okay, on a mathematical level, I would like to say, because again, I am mostly using what Mathematica can do for some specific purposes, not necessarily trying to build the ultimate hypergraph rewriting framework. Maybe Nick wants more that than I do, but I certainly am thinking of this as so there's only really information on a vertex if you label it. So if there are vertices that are unpopulated in some sense, the system somehow doesn't track it. And so in particular, you can imagine, you could just write this rule in which this vertex is deleted, and it just disappears. So the convention for me is that normally I would take hypergraphs to exist on a set number of vertices that you set, and it doesn't change. It's kind of this sort of data locus, data places where things can be populated. But the rewriting, even though you can technically delete them, for me the data is not really lost, because if you begin with 300 vertices, they're still there, sort of as your memory slots in some sense, right? So I think the answer is you can delete, but in my personal usage, I am considering that the vertices themselves are not important to delete or not, because the information is only if they carry labels. in that sense.
I mean, there's like two potentially interesting observations one could make from the rewriting theory side.
Right, right.
So, I mean, in principle, so if you look at chains of rewrite rules and sequences of applications of rewrite rules, like derivation sequence, as you show, there is an associativity built into the compositions of the rules themselves. I mean, if you look at any of your trees, you look at two steps, you normally can just visually inspect that there's a composite step you could do.
Yes.
And my suspicion is that, and this I mean, this is something I discovered. It's like concurrency is this possibility. I mean, the entire theory of concurrency tells you how to extract this one-step rule from two derivation sequences. But I mean, the properties you want to show typically would involve n steps at which you can compare. And that is, I mean, so happens to be called associativity theorem, which holds for double push-out writing. But once you start to modify the semantics, you might break exactly that property. So, I mean, for that reason, it's good to understand what is the precise semantics you're using, which is something I discuss already with the other guys from the Wolfram project. Because, I mean, at this point, you would artificially lose some property which you want, namely that you can, let's say, compositionally reason about steps. Because here, I think your proof of, I mean, I think we should be careful, the associativity property that you encode in a given rewriting system. So, I mean, it's on the face associativity, say, for an associative algebra. The proof of that is presumably that up to isomorphisms in the labelings, you find n-step sequences that are directly comparable for input and output. You want the entire relation to be compatible, right?
Right.
And so it's presumably more efficient to search on the compositions of rules than on exploring the state space of the grammar, because if you in the end exactly want to extract these sort of closed loops.
Right. So that's one of the things that I was pondering, because my intuition has been that the information is somehow more on the states and not so much how you reach them in this sense. Because if I, of course, how you reach the state defines the label that you carry in that state in the way that I've been presenting it, right? So although I've been using just terms in Mathematica here in this language to express the rewriting, but in some technical sense, I think what I should be doing is that every rewrite takes, because of this subtlety that I mentioned, that the kind of data structure that I impose on the output label kind of knows about the input hypergraph, right? So it's this mixture of the labels really don't have an independent life of their own. They really sort of know about the structure of the hypergraph. So what I think I should end up doing technically is that you label the edge with the hypergraph itself. So you take that hypergraph, that local match, the O, right, and you, so the I of the side of the rewrite rule, and you label that particular instance, that inclusion of the I in the edge. So if you keep on going with that, then you have a history of your rewrites on a single edge potentially, and so the statements are of the form, these two histories arrived in the same place in some sense, and so those two histories are to be deemed equivalent somehow.
But that, again, that's just an artifact of working with states. So if you were to use the composition of rules operation, and I mean, that's not technically easy to implement, but if you were, then you would precisely not have to worry about these relabeling problems. I think some of the artifacts you have with these very large graphs come precisely from that you insist on looking at the transition of states, which is and there's a combinatorial explosion, because you typically have a number of ways to reach the exact same initial and final state. So I mean, that might be worth looking into. And I mean, a completely different direction actually has nothing to do with rewriting theory. So, and that's another reason why I ask whether you delete things. If you indeed do only push outs to do your derivations, you're probably technically very close to working with what's called a sketch and sketch operation. So, I mean, that's actually a completely standard technique in category theory. For example, if you want to encode a monoid or associative algebra or whatnot, there is a technique of precisely coding that in diagrams. So, I mean, for the moment, what you've showed at least looks very much like what's called sketches.
Okay, right.
In the theory of Mackay. I'll send you some links because
yes,
that is something very standard but not very well known.
But is rewriting of sketches.
Well, it so happens that if you take push-outs along sketch morphisms, that exactly emulates, double push-out rewriting where you only add structure. If you were to delete something that is slightly more intricate, there exists
there were cases where there was stuff deleted. I mean, there was certainly cases where edges were deleted here.
Yeah, but I mean that still is just a push-out. I mean, you don't need.
Right. So I'm curious. I really want to look into the sketches because that sounds very.
Yeah, I'll think it's unfortunately very unforgiving literature, but I mean, we are studying this currently in the Scoriac project because we want to do proofs with it. So I'll send you some pointers, and we.
But I wanted to go back to your comment, Nicholas, about because I'm curious. How do you imagine being able to spot this sort of pattern that so far I've seen as state-based in the sort of compositional associative view of rewrite rules? How do you imagine it will show up?
Well, so it's precisely this feature that I mean, if we study chemical reaction systems, for example, where where it's very typical that the state space is very combinatorial, like in your case. Mm-hmm. So there's techniques of looking at, for example, the pattern you wish to observe. For example, is it can. Let's take the simplest one where you want to have simple involution that you can arrive again at the same state, let's say up to potential relabeling that has to be discussed. But I mean, you can then look at a commutator, you can look at pre and post composition with the rule and see if it sequentially, well, not sequentially, if it can be matched on both sides, then you have an observation. So I mean, this way you can define what it means to have sort of these 2 points in your view. You would have the start point and some end point, which you can compare, and then you can study what's the internal mapping in that composite rule. So, but I mean, to say that the implementation effort is in implementing the direct composition of rules. That means a little bit more effort because you need unification of rules and so on.
Right.
I think maybe from this point of view here, I mean, relating to what Carlos said earlier, the difference would be that you're not starting by generating all the possible start graphs.
Yep.
With I can't remember what it was, nine nodes.
Yes.
A couple of millions of them, but you're basically generating all interesting ways in which rules can be composed.
Mm-hmm. I see. Yes, that makes sense. Yeah, exactly.
So
which has starting from
the opposite end, and maybe you can put constraints on that and say, I don't want to generate any rule compositions that contain graphs that have more than 9 nodes in them or something like that. But you're sort of driven by the rules rather than by the states in a way.
Right. So that's very interesting. But at the same time, I want to make sure that I live with the right intuition, because I will definitely read further into that, because I did read at some point, but I thought, okay, I need to really get the essence of it and to get the strength to go into it fully. So the intuition that I'm getting right now is that I will be looking at how the rules. So for example, if I'm studying something like the fish or the Bhattacharya-Messner thing, where there's really one single rule, right? I would imagine that what is happening is that approach is going to tell me about the rule interacting with itself.
Exactly.
Right. So.
And you could take advantage of all of the symmetries in your problem. Because,
right. And so the issue is that sounds exactly relevant, because in a way that's exactly what I've been trying to do. So in a sense, I've even though I've been showing states and looking at the state graphs and all that stuff, my interest really is how the rule interacts with itself, because I am in some sense deeply assuming that the rule is the algebraic content of the theory in some sense, or it spans the algebraic content in some direct way. So I would really want to understand the details of that, because I think that I wonder how that is going to make the process different in some sense, in that how checking how the rule interacts with itself seems to take the rule as the starting point instead of searching for initial states, right?
You're essentially doing what I call tracelet analysis. I mean, for example, here in this rule, I would suspect there's some combinatorial structure because, I mean, the way you draw this rule, it looks like you could take 3 copies of the rule and basically plug the output triangle. Sorry, you need 4. The output triangle in the 3 possible ways onto the smaller triangles. Yes.
Yeah.
So you take one of, you take one of the rules you show as the last one, and then onto all the triangles you plug one of these triangles here.
Yeah.
And there is then 3 equivalent, combinatorial number, 6 ways in principle to choose in which sequence you plug, all of which lead to the same composite rule.
Right.
So that is one symmetry your system has. But I mean, it's just that the viewpoint is much more constrained in the number of you see much better the combinatorics. Actually, it has to do with that double push-out rules do form a rule algebra, and that is carrying all the combinatorial information you can ever discover on the state space. So I mean, in chemical reactions, for example, if you just have creation and annihilation of vertices, there's exactly one causal relation, which is you can delete a vertex you just created. But I mean, you also get the number of combinatorial ways to do so. In this case, just one. But I mean, so that is exactly for these sort of mathematical analysis. The price to pay is you have to somehow develop an algorithm to keep track of these rule compositions. So in a way, the state space view is maybe easier to implement.
Right. So I guess you could, once you devise the algorithm, you would essentially start from the rule itself, and it grows from there, right?
Yeah, and you would try to analyze the structure of these composites.
Exactly.
Tracelets.
Exactly. Yeah, tracelet. Yeah. I was in my reading list, so now all the more relevant.
I mean, you can plot out a tracelet as a sequence of transformations of graphs, because in the end of the day, a tracelet is just a minimal way of computing a sequence of transformations, where basically the overall input is the minimum motive you need to fire the sequence of rules, so to speak, in that particular causal order. So in a way, you can, once you have a tracelet, you can plot it like a little transition sequence.
Right.
The question is how to store the data structure. And as I said, like the price to pay is you have to implement composition of rules, which is a non-deterministic thing, because you can compose by forming partial overlaps of input and output.
Right.
So I mean, it's not. I'm not saying this is immediate. It's just that for this sort of search, it might be useful to have.
And Nick, can I ask something? Which is, what is the difference between sketch rewriting and graph rewriting? Did I understand well that you distinguish between that? Because when you're replying to Carlos.
Yeah, there is something about, at least in the basic theory of sketches, where it is very well understood what it means to take a push out. So basically, a sketch is, in the very simplest setting, just a graphical structure, which you can interpret in a category. You can make a model of a sketch in a category. So in the simplest case, you just have exactly a graph, and then you basically, for example, have the signature of a directed multigraph, and then you have a model of that is an actual multigraph. And then if you find an embedding of a motive, like here, like the left-hand side, into a graph, and you have a morphism from that, like here, it's not an inclusion, it's like it is an inclusion up to the vertices, but not for the edges, then you can take a push out. And so if that is the operation you're happy with for your particular application, that has an immediate meaning in sketch theory as an extension of a sketch. And that usually is used for doing proofs with sketches. So I mean, I'm saying there's an entire mathematical formalism which is independent from graph rewriting, and which has been developed in France by Eresman, and then in the States by Wells and Barr and Wells. Sorry.
Yeah. This is actually not so bad. There's a nice book by Barr and Wells about category theory for computer science or something like that, which is quite readable and has a lot of the kind of basic concepts of sketches are actually there, and it's quite accessible. So I mean, some of the original papers are hard work, but that is actually a textbook that you can just read with a bit of background from one end to the end. So maybe my way of explaining the difference would just be that graph rewriting doesn't care in general about the meaning of the graph.
Exactly.
It's purely syntactic in a sense. You're rewriting a graph. The graph is just a structure. And if I talk about sketch rewriting, I mean, it's not even a technical term, I would say. I mean, it's something that is, in principle, you can do, but it's not as such an established term. But the sketch is a graph that is interpreted in a category. It's basically the graph of the diagram the shape graph of a diagram in a particular category.
Right.
And so you basically have sketch rewriting means that you're rewriting graphs that are essentially diagrams in certain categories. That means you're working. I mean, the rewriting is still syntactic, but you know what the semantic domain is. Graph rewriting in general, the graph can just be itself basically without having any interpretation or any semantic.
Right.
Yeah.
And I wanted to ask, are you aware in that literature if they explicitly cover hypergraphs as the domain?
Yeah. Because you can essentially take, I think the reason this is quite difficult to read sometimes is that it's very powerful. So I mean, some of the later iterations of that theory can basically take any two monad and construct a data structure over it, including all sorts of hypergraphs. And even if you can encode dependent type theory if you must in very general kind of sketches. So I mean, the literature is hard to read because mathematicians precisely in category theory use sketches to classify all sorts of algebraic structures. And so I mean, it has been used in computer science. It then was more used for database theory. If you want to explain what's an SQL query, that's done in sketches. I mean, it's I'm just thinking to myself that you presumably have more this interpretation in mind, so it might be worthwhile having a look. I don't know about these Higher-Arity operations. It was useful for that, but hypergraphs for sure. Yes.
Right. Yeah. All right. Yeah. Thanks very much.
But the hypergraphs are not the hypergraphs could be in the model category, right? They're not necessarily in the
well, you can take
in the schema graph.
Well, the schema can be any kind of categories satisfying certain minimal requirements. And what I understand is that sort of, I guess this minimal requirement is at least being locally Cartesian closed or something like that. So you have all sorts of quasi-topoi, which would fit that bill. So in particular, all sorts of hypergraphs, I guess.
Okay. No, I was thinking much more of the sort of more traditional sketches where the schema is just there
it's graphs. That's
just
true. That's
graph rather than a hypergraph. But you're right. So this generalizes to more kind of complex.
I mean, I have a few references I can send you, Carlos, where, for example, somebody explained how to develop the theory of monoids in this graphical way, which might be closest to what you're interested in.
Right. Yeah, I appreciate that. Yeah, absolutely.
And we have a meeting on March 12th, I think, where we will discuss some of this. So we are interested in that because we want to develop a formalization in proof assistance for consistent graph writing. So sketches happen to be the only most general enough concept one might be able to use to do proofs on graph writing systems. So for that reason, we are currently investigating this, so I can keep you posted if you.
Oh yeah, absolutely. Yeah, I'd love to be in the loop. Yes, absolutely.
Yeah, by March 12th, I might be able to tell something more concrete.
Nice.
I'm still learning this myself.
Will it be online as well?
It can be. So yeah, let's yeah.
Yes, yeah, absolutely.
Okay. Well, should we close the official YouTube discussion, or?
I think so.
Yeah, let's do that. So thank you very much again for your talk, Carlos, and
my pleasure.
Everyone else for attending. And yeah, we have an announcement for next seminar.
Yes, in 2 weeks we have Arend Rensing again, who will show us some more advanced features of this Groove tool for graph writing. By the way, might be also interesting, Carlos, to have a look. That's the sort of in our community the longest standing platform there is for doing graph writing, but not sure if it can do hypergraph.
Model checking tool for graph rewriting.
Also, yeah.
So state space exploration and model checking.
Oh yeah, absolutely. Sounds very relevant.
Okay, so I'll close the live stream now. I don't see anybody left on YouTube at this moment. So thanks a lot, Carlos, and